Hello, everyone. We are starting our fifth lecture on the event Artificial Intelligence Applied to Geosciences. The event consisted of one lecture per week on AI and its applications in some areas of geosciences, including potential methods, so seismic interpretation, petrophysics, seismology today, and astronomy. You can check the live recordings here on the channel. Two of them are no longer public, but the others can be watched here. And today's lecture is with Dr. Josipa Majstorović. I'm pretty sure I butchered the pronunciation. Dr. Josipa obtained her PhD in geophysics in 2019 from the University of Strasbourg, and she is currently a postdoctoral researcher at the Institute of Earth Sciences at the University of Grenoble, and she's a member of the European Research Council Monifaults project. As a part of the project, she's developing deep neural networks for earthquake detection, localization, and characterization. And I'd like to thank very much Dr. Josipa for being here with us today. And apologize again for botching the pronunciation. And you can start the presentation and talk a little bit more about yourself. If you go to your presentation, I'll put it on the screen.
So I am okay. So now it's full screen, right?
Yes. All set. You can start.
Okay. Thank you, Isabella, for this nice introduction, and also thank you for the invitation to give talk in this series of events. So hello, everyone. My name is Josipa Majstorović, and in today's talk entitled Artificial Intelligence Applied to Seismology, I'm gonna follow this outline, meaning that I will have two parts of the talk. In the first part, I will kind of give you a short overview of what has been done in terms of artificial intelligence in seismology. And the second part will be more my contribution to this topic, so from my point of view. So let's start. What is artificial intelligence? And in a very broad sense, it's a wide range of methods or computing system which are capable of performing tasks that humans are naturally good at. And here in the middle, you have a list of some of these methods, such as rule-based systems and so on. And then if we focus just on the subset of the methods within the artificial intelligence that are named machine learning, we are talking about collection of statistical methods that enable computer system to learn from the data. And some of these methods are support vector machine, decision trees, k-mean clustering, and so on. And then if we go even further into this machine learning methods, there is a subset of methods called deep learning, which are a collection of neural networks or biologically inspired networks that extract abstract features from the data in some hierarchical fashion. And in this, for example, some of these methods are recurrent neural networks, convolutional neural networks. In my talk, I will mostly base on these machine learning methods and deep learning, since I've been working with them mostly. And so I would like to talk further a little bit about machine learning. Okay, sorry. So it's quite important to know that when we have a problem in machine learning, it can be solved either in supervised or unsupervised manner based on what kind of data you have. So if you have a label data, then you will probably solve your problem in supervised manner. And in the case you don't know nothing about your data, you would go for unsupervised way. So when I say label data, it means that labels can be anything. So let me give you an example. If you have pictures of cats and dogs, they can have labels that are, like words, cat and dog. You can have, for example, prices of apartments in New York, which have some characteristic, and you have associated, these apartments with a price, and this is like a quantitative label. And so in terms of these different labels, you can solve your supervised learning in a category prediction or quantity prediction. So as I give you an example, if you have a category, you can predict like something, having a cat or a dog from your pictures, for example. Or if you have a quantity as the price of an apartment, you can predict or have an algorithm that is supervised that will tell you the exact price of the apartment based on some features of this apartment. I mean, when I say features, for example, when the apartment is located, what is the size of the apartment, or so on. So, and for each of these supervised learning prediction, you can have specific methods. And I will mostly base, so I will further show you an example of supervised learning and more precisely a classification of supervised learning. When we talk about artificial intelligence in seismology, it has very long history. And one of the first works I'm showing you here is done by Doula and collaborators in 1919. And basically, they used artificial neural networks to develop a model that is able to distinguish between natural earthquakes and underground nuclear explosions. So it's kind of, I mean, simple task that even in that time, like 30 years ago, was solved. At least they tried to solve it by artificial neural networks. And then from this, year on, there has been many things happening. And here I'm showing you a graph where on the x-axis you have years, and on the y-axis you have an annual rate of publications in the topic of earthquake predictions. So using a neural network for earthquake predictions. So you can see that, how the years are passing. There are more and more interest into artificial intelligence applied in seismology. If you are more interested in reading, I would recommend this paper by Bergen and collaborators in 2019, where they very nicely wrote an overview of machine learning methods and how this and how a specific method was applied in, for example, in seismology or solid earth geoscience. And there's another paper by Kong and collaborators in 2019, where they took some seismological research topics and they really nicely wrote an overview what had been done in solving these specific research topics. I will use basically this second paper to give you kind of flavor of some of these papers. And a little disclaimer, none of these papers is not like the latest development in this specific research topic. Is something that I found interesting, so I want to share with you. So let's start with the Earth prediction. So earthquake prediction, what we call the grail of seismology. So the problem or the goal of this studies is to have a model that is able to tell us when the earthquake is going to happen. So it's not solved problem yet, and I don't even personally think it's going to be solved anytime soon. But it has been shown that laboratory earthquakes, so earthquakes that are simulated in a lab environment where you can, record the input and the output acoustic waves. So it has been shown that this kind of earthquakes can be forecasted or predicted. And there has been an interesting paper by Johnson and collaborators in 2020. They wrote an overview of the machine learning competition, where they used this subset of data from one of these lab experiments and developed many forecasting deep learning models to solve this specific problem. And it's quite cool because they actually provide all the codes. So it's really a case study for this specific problem. Next, we have our earthquake detection and phase picking. This is quite important topic in earthquake, in seismology, since you want to have a model that is able to scan the data very fast and for example, historical data or whatever. And in this data, to have a model that is able to scan the data and tell you when where is the earthquake, and also to kind of associate specific arrivals of P and S waves. And there is an interesting paper that also came out recently by Musava and collaborators, where they developed this earthquake transformer. So transformer is a really specific deep learning model, which is able to simultaneously detect and phase peak seismic arrivals. So this is kind of one way to solve this problem. Of course, it is not. Even though it sounds very easy, it's very difficult, and so there are still progress in this research area. And I will show you, for example, my contribution in this part. Next, earthquake early warning and real-time machine learning topic. So the main goal in this studies is to have a model that can tell you just based on the first, let's say, 4 seconds of the P arrival of the S waves, whether the earthquake that it's happening at the real time is going to be big or small. And based on this estimates, kind of give out the early warning system for a possible tsunami, for example. And I found this paper interesting by Kong and collaborators. They developed the MyShake deep learning model, where they use a seismic network of smartphones to provide this earthquake early warning system. So based on quite interesting deep learning models. Next, we have a ground motion prediction topic. So the goal of this study is to have a model that can tell you that based on like a specific of some soil ground, what will be the maximum ground motion. And this problem, for example, have been mostly solved in a linear regression manner. And even though it sounds also kind of easy, it's complicated. And because the data are not really, the data are sparse. And here I'm showing you, for example, one work by Terre and the collaborators in 2012. They used neural networks to predict P ground acceleration by using data such as distances of the earthquakes, magnitude, frequency contents, site locations, and so on. And the last, we have tomography and geophysical structure research studies, which is quite important because the goal of these studies is to give us a image of the geophysical structure, below the surface. And in classical manner, these problems are kind of ill-posed because the data are kind of noisy, and you use inverse algorithms, which are quite difficult one. And so I found this work interesting, where De Mosley and collaborators in 2018 used a deep learning model to simulate seismic waves, and quite fast, and then use these simulations to do some inversions. So I hope I gave you kind of like this short. I hope that this short overview kind of convinced you that there are many things going on in seismology in terms of artificial intelligence, and even though many of these problems have been tackled, they're not completely solved. Next, I would want to switch to this specific problem that I have been working on personally, and this is detecting earthquakes or small seismic events. So let's go from the beginning. So when the earthquake happened and it is recorded on stations, In a classical seismological approach, there are some like automatic algorithms which would scan the data, and based on amplitude frequency content, it will kind of give you an alert. Okay, there have been an earthquake, and then usually what is done, seismologists would open this data and manually check if there is an earthquake, and whether if there is an earthquake, he would manually pick the arrival of P and S waves. So you can see that this is quite tremendous job, especially if there's a lot of data coming on, especially if there's a lot of stations and so on and so forth. To be able to locate where this earthquake is coming from, we need to at least have 3 stations. Why is that? So it's because, for example, if you have an earthquake that happened on station A here, you can define this radius based on the S to P time arrival. And if you do this for 3 stations, you can see that then we have a unique location, which we call the earthquake epicenter. Once when the earthquake is located, we can put it in some kind of base, which we call the catalog of earthquakes. And here I'm showing an example of Italian catalog of earthquakes. And this is kind of one of the main products of seismology, so having the catalog of earthquakes, because then we know when the earthquake happens, what was the magnitude, and when where on the Earth's surface, or for that matter, also in depth. So having this information about where or when the earthquake happens, we can statistically infer maybe what would happen in the future, or which areas are seismically active, and thus maybe how to say, they are not difficult to live there. So, for example, if we know that there is a very active seismic area, then we know that this area is probably very dangerous to live there. So the problem is, what if you have an earthquake that is only recorded with 1 station? So in that case, you cannot use a classical approach of this triangulation method to locate the earthquake. And it has been actually shown in numerous studies that most of these catalogs miss some events, particularly small magnitude events. The reasons can be because they are too small, or because you don't have enough stations in the specific area. And also now there's a trend in seismology where, for example, this paper from Brodsky in 2019, it's shown that it's quite important to actually study these small earthquakes that we were omitting for years in our data, because these small earthquakes are kind of give us information. What is the reason why the earthquakes happens, and they might constitute even some, let's say, precursory phases before the large earthquakes. So this is something that is currently under the studies, and many people go in this direction of studying small earthquakes. So the challenges are how to improve catalogs by detecting as much as possible these small earthquakes. Also, the challenge is having only one approach, so approach where you can use only 1 station to detect these earthquakes, and at the same time having a model or algorithm that is able to scan this vast amount of data. And so I would like to talk about this method that I was working on, and this is a convolutional neural network for earthquake detection and characterization. To kind of in this work, we try to tackle some of these problems or challenges. So this has been work I've been working for 2 years, and I would like to give you an overview what it actually takes to develop a deep learning model. So what it takes to go from the data to some extended catalog. And we will follow this outline in which I will try to convince you that this approach is highly decision-making, where each decision you make might affect your results. So let's start with the study area, or what was our main motivation to start this research at first. So the study area is Italy, or more precisely the center Italy. Since in 2009, there was a big earthquake, a L'Aquila earthquake, magnitude 6.3, which was quite devastating in terms of human loss, but also in terms of material damage. In scientific manner, it is quite interesting because the earthquake itself was preceded by 4 months long foreshock sequence. So it means that, there was a sudden burst of seismicity just 4 months before this earthquake. Then we had a main shock, so the main earthquake. And after that, almost 1 year after this area around the earthquake, so you have it, the epicenter here, was kind of quite active. But when you look at the catalog of this area, so specifically of this red zone here, you can see that before 2009, so before this year of this earthquake, you only have around 100 events. So the question is, like, what is actually happening before 2009? I mean, was there something happening? And if you want to look at the data, if you want to go back and locate some earthquakes back in past, you realized that there was only one station recording for years before 2009. So there's no way that using some classical seismological approach, you can go back in data and see if you missed some events. So there was this need to define a model, to design a model that can use the single station approach to scan this historical data. And we try to find the help in the deep learning. So having 30 years of recorded seismograms at the station, that is actually, yes, I forgot to mention, the station is very close to the earthquake. Next thing that we needed to do is to define what methodology we were going to use. And we decided to use convolutional neural networks, which is, if you remember the previous slides at the beginning, a supervised learning algorithm, meaning that you have to have an input data which are labeled. Just as in this graph, so for example, if you have pictures of a car, then you have a label for this car, and you have a model that is trying to learn a connection between the pictures and these labels. If you want to predict, for example, in this case, what is a car, and if you want to have a model that is able to predict between a car, truck, van, and bicycle, it means that you need to have a data about all these labels. In my case, so the input data are not pictures, is actually time series, and it was actually earthquakes. So earthquakes that was previously recorded at the station. So the next step for me, or the first step to be able to train any kind of deep learning model, is to have a data, and so to generate a database. So we knew that the first input layer in our CNN, so the data that we are going to use would be a time series of our earthquakes. In our case, It is a three component. When I say three component, it means that I have a recording that my data are consist of the time series in the east and west direction, north-south direction, and vertical component. And so I have this, I need to generate a lot of this type of input data. So I have to have a database of events. And how I do that is that I use the existing catalog. And using this existing catalog, I can go back and look at the data, at the seismograms. So now the question that we ask ourselves is how to build a good database of these events to be able to go back, to be able to distinct, only events in this small area around this station. So to be really extract events that are associated with the fault that was responsible for this earthquake. And so to do this, we realized, okay, we need to use all the earthquakes that ever happened. And for this purpose, we merged several existing catalog. And we end up with almost 500,000 events. And we took each of these 500,000 events and select some criteria, what is the optimal earthquake for us, and ended up by having a 65,000 accepted earthquakes once when we look into data. So these 65,000 events consist, define our database. But if you want to use your deep learning model to scan the continuous data, you're also aware that there is a lot of noise. So, basically, there is 90% of your data is basically noise. So it means that you can not only use earthquakes, you also have to have a noise data or a negative sample, what we call here. And so complementary to your database of earthquakes, we also need to extract a database of noise. And this will kind of represent what is happening with your data. And you can use this to train your deep learning model. Next, so when you have your database, is to define a framework. So what I mean by defining a framework is that you need to go and specifically design how your model is going to look like. For example, if you consider a task which is a detection, and when I say detection, it means that having a model that knows what is an earthquake, what is a noise, what is an earthquake, what is a noise. So it's a quite binary problem. You have earthquake noise, 0, 1, positive, negative. So in that terms, it means that you are solving a classification. So just predicting a category. But if you remember that our goal was to extract events associated with the fault. So it means that we also not only need to detect earthquakes, but we need to characterize them. We need to give them some kind of labels, let's say distance, which we can use to distinguish, exactly what we want. And so it means that we have to also have a characterization model in which we would have labels like a distance and magnitude. And if you remember this story from the beginning, where we have, pictures of cats and dogs, which are category, and we have prices of apartments, which is the quantity. So it's the same here. So the distance and magnitude are actually quantity, but you can solve this also in the classification manner, as well as you can solve it in the regression manner. We choose to solve it in a classification manner just to see whether we can, whether we can actually solve this problem at all. Like a regression would be a much difficult task. So once when you define, okay, so I need to have a detector, I need to have a characterization. Next step is to define whether you want to solve this task, separately or together. I'm not going to get very much into the details, but the point is that you have a freedom to define whether you would have a detector and a characterization model as part of one model, so that your model detects and characterize at the same time, or you can have two models. Also, if you are solving a problem in the classification manner for a characterization, you need to define a class. Since distance and magnitude are continuous variable, you need to define, a threshold. And defining this threshold differently going to affect your result. In our case, so we have a specific, idea in our mind. We want to isolate events that are close to the fault, so that are less than 10 kilometers from the station, and having events that are less than 10 kilometers from the station and that are far away. So kind of this idea helped us to define these classes in a way that we wanted. But you can define this, whatever you want. You really have freedom. But you have to be aware that this choice will affect your results. So once I define that I want to have a detector and a characterization model, this is how my pipeline looked like. So I had a two-stage pipeline for earthquake detection and characterization, where in first stage, I train what I call a CNN detector model, which is taking earthquake samples and noise samples, and as an output is giving me detector probability. So this model is going to give you basically it's going to give you a value. If this value is 0, it means that my model is predicting a noise for a particular time window. If it's a 1, it means that it predicts earthquake for a particular time window. In the second stage, I train a CNN characterization model, which as an input is only taking earthquake samples. And as an output is having distance probability and magnitude probability. Where distance probability, it would have 2 outputs in my case, and for magnitude 4 outputs. So what it means, so for example, this earthquake, if it's really, if my model is trained well and this earthquake is close to the station and have magnitude, for example, 1.5, it means that my probability for this class would be the highest, as well as for this class, while all the other classes would have very low probability. So having this framework finally defined in our heads, next step is to train, validate, and evaluate our models. So in machine learning, that is very common that you have let's say, 2 steps. One step is the training validation of your model, and the next step is evaluation. For this purpose, your data is usually divided in 3 data sets. So, in the called training, validation, and evaluation data set. So where evaluation data set is really saved for the final step, meaning that you would use your model and use this data to really see how your model is generalizing. So it's showing a data that you've never seen before. But in the training and validation step, your model is going to see this data, a lot of times. It's like an iteration process. And so it's quite important to have this data set defined from the beginning, so that basically at the end, you know how well your model is generalizing to the unseen data. I'm not going to go too much into details of this process, but I'm just going to mention that the training validation is depending of a lot of hyperparameters. One of them are associated with the parameters of your architecture. For example, just to mention, just to give you a flavor, like how many neurons you want in your architecture, how many layers, what type of layers, so on and so forth. And there are second group of parameters, hyperparameters, which are associated by the learning process and, for example, learning rate. And what would you commonly do? It's a brute force of all the combination of these parameters, where you would basically perform a grid search to find the best model. So, for example, you decide to test 10 parameters of the architecture, 10 parameters of the learning rate. It's going to be like already 1,000 models that you can define by the combination of these parameters. And then performing a grid search, you can, like looking at the accuracy of your model, you can find the best model. So I'm not going into details of my analysis for this matter. I'm just going to show you results. So it means that after I train my model, so the next step is to use this model and apply it on the evaluation dataset. And here I'm showing you results for my CNN detector. When I put very high threshold on my output probability. So this is commonly called the confusion matrix. And on the x-axis, you have predicted label, while the y-axis, you have a true label. So how do we read these plots is like my model was basically able in 100% predict a noise window when the true label was a noise. And in 76% of the time, it was able to predict signal when it was actually a signal. So you can ask me now, okay, are we happy with these results? I mean, the problem itself is quite difficult. And I personally was happy with these results. Why? Because once when I would apply this model on the continuous data, it means that my model would actually not predict noise as a signal, because this part, is 0%. But it would mean that I would probably miss some signals, because some signals would be predicted as a noise. But this means that I would actually have not a lot of false detections, and that is was important in my case. Next, I will show you results for the CNN characterization, and this is quite tricky. And this problem is even more difficult to solve than the detection. So here you have two confusion metrics. The one on the left is associated with the distance, and one on the right is associated with the magnitude results. So we can see that, when it comes to the distance, because it was only two-class problem, model was able to actually learn how to distinguish let's say signals that are close to the station and those that are far away. So in 87% of the time, my model knows, that the event is close to the station when it actually was, close to the station. And in 97% of the time, it would predict far away event as being a far away. Magnitude, quite complicated, and what is good is that maximum values is actually reached on the diagonal of this confusion matrix. So it means that most of the time, not 100% of the time, model is able to classify the earthquakes based on the magnitude to the true classes. So okay, so you train your models you are happy with your evaluation, next step is to apply this to the continuous data. And I'm now going to show you how this can be done. So here you can have here what you are seeing is basically time series, where on the left you have the amplitude of the seismogram, and on the right you have a detector probability, and on the x you have a time. So what you see, so in this orange is actually this probability that that my model CNN detector is giving me. And you can see there's quite a lot going on, and defining a threshold is quite important. So usually what is done is that you would put a threshold at 0.5, so something here on the middle, and everything that is above, so each time step that have a probability higher than 0.5 would be declared as a detection. In my case, I put this threshold quite high on the 0.99, so that I'm really, really sure, or let's say that I only consider those events where my model is really, really sure that this is a signal. And then basically, for each of this time step where we have a high detector probability, I can extract magnitude and distance class using my Cnn characterization model. Here I'm showing you some of the new events, so the events that didn't exist in the main catalog for the February 2009. And again, on the x-axis you have a time, on the left axis you have an amplitude of the seismogram, and on the right axis you have the detector probability. So imagine that this this window defined by this green line is like a slide window, and you take this slide window and scan your time series. So the moment when this time window catches the earthquake, this probability is start to rise, and basically the position of this first green line is associated with the maximum detector probability. Yes. So it's telling me, okay, so now when we have this position of the time window, this is where we see an earthquake. So you can see how this probability is starting to rise, how this windows start to catch the earthquake. So once when we scan our 30 years of data and we put this high detector threshold, we put the high threshold detector probability, and we extract so the classes using our Cnn characterization model, we can basically only extract the local events. So the local events by being the ones close to the event, so less than 10 kilometers from the station. And here I'm showing you all the detections in blue, in the form of a cumulative sum over the years that was relieved by my two-stage CNN pipeline. And what is really exciting is that we do catch some events before 2009 compared to the reference catalog. So the reference catalog is the one that I used at the beginning. That, if you remember from the beginning, I told you that this catalog had only around 100 events before 2009. So we do catch some new events. What is important to say that, for example, this two-stage CNN pipeline is able to scan one day in 2.5 seconds. And luckily, for example, my data were divided in 4 groups, like in 4 periods of time. So I was able to continuously scan these 4 periods of time. So I was able to obtain this catalog in 3 hours. So you see the power of these CNN models. So, being able to have this information in such a short time, and also, how to say, being able to actually catch some new information by using only one station. So we have to remember that this is only using one station. Of course, research or study doesn't stop here. Now, the next step is to analyze this catalog and see if we can see some patterns before and after a L'Aquila earthquake. Also, some things that we have been doing is to, for example, see how the different databases affect the results. Can we do better with the regression model? I remember I showed you this decision when we had to use classification or regression model for our earthquake location. And something that I have been working recently is, can we understand why CNN is working the way it's working? So can we explain the black box nature of our model? So you see there's a lot of things going on, and it's a quite interesting topic. And with this, I would like to finish my talk. I hope I convinced you that machine learning or artificial intelligence is quite an active topic in seismology. Many problems have already been tried to be solved and tackled, but there's always room for improvement. Just because the deep learning models are highly decision-making, and they are very adjustable. So you can really define your framework, you can really define database differently, and this would affect your results. From a personal point of view, I maybe didn't mention, so I have been working on this for 2 years, and before I started working on this topic, I basically didn't have any background on machine learning. So I really encourage young people, if they are interested in this kind of stuff, to really go for it. And that's it. Thank you for your attention.
Thank you very much, Josipa, for the presentation. It's very nice. Can you hear me well?
Yes, I can hear you. Yes.
Oh, okay. It was quite interesting. Unfortunately, I had an internet connection problem, and I didn't get the first part when you were saying about the applications in general.
Mm-hmm.
But it was quite interesting. I thought it was interesting your comment right now that you didn't have any knowledge on machine learning previously. So in 2 years, you started learning and applying.
Yes.
It's quite good.
Well, it was quite intensive, but I'm not alone. I had a machine learning expert in my group, so working with her and with some other people, it was possible. So that's why, from my personal point of view, I really encourage people to, start digging in or asking around this kind of stuff if they find this interesting.
Yes, but you had knowledge on programming, any programming language?
My master was in seismology. My PhD was in seismology, a bit specific topic of seismology. And during my master and my PhD, I was coding. But the thing about machine learning is that there are many tutorials, many codes existing already. For example, as I give you this paper on machine learning competition, all these codes, I think there are 400 or 500 codes existing to solve this problem. And also what is cool is it's kind of transfer, you can transfer the knowledge from the other research areas to this for example, to seismology, because the models are quite general. You would define input data differently, and you would define the output the way you want, but the CNN, the architecture, the layers, they are already exist, they are coded, so it's really easy. Maybe, I didn't mention in my talk I use Pytorch. So it was quite intuitively to use Pytorch, and having all these tutorials and is I mean, of course, I don't want to say it's easy, it's completely easy. There's still work, you need to put an effort to study this, but it's possible.
Yes, the interesting part that like I said, there's a lot of information available already. So starting in machine learning, I mean, in any programming and machine learning, it's hard, obviously, when you start from zero, but you can do it with a lot of help from people online.
Yeah, I think maybe what is also overwhelming is that there are a lot of there are a lot of data out there, and it's good that you maybe have someone who can point you to some good tutorials or some good references. That's true. Like if there is someone who already passed through some this process, he can show you, okay, listen, this is cool tutorial, please use this, or this paper is interesting because they provided the code, you can start from this. I mean, I did start for example, the idea for our paper, we based on already existing work in that has been done, and so you already have a reference, or you have a kind of benchmark model that you start to work from, and then you can build up on this. So you don't really, I mean, you start from the zero by learning, but there's some kind of benchmark model that you build on your model.
True. We have a question from Mariana here on chat. She asked, in your research, apparently magnitude was the parameter with the lowest quality in the evaluation, right? Any specific reason?
Yes, I mean, there is to estimate the magnitude, it's very difficult in seismology. It's usually done based on the amplitude. And I mean, what I didn't comment in my talk is that having a data that is quite good is quite important. But in seismology, we already know that we have some problems, and then there are some biases, that some, some parameters like magnitude are not very well estimated. So, this will make the problem itself difficult, because if you don't have a good quality data, I mean, the problem is going to be difficult to solve. So a lot of things in machine learning really depends on your database. That's why I was saying that detecting earthquakes, it might seem easy, because there you can see them in the data, but the data, the labels are not good, that what we have so far, and they are sparse. So these are kind of problems we are dealing now in seismology.
True. You showed in your presentation a part where you said that you have to take the noise of the data, right?
Yes.
But you said you filter it afterwards, or you just you kind of collect the filter, just to see if I understood. You collect the noise and also the data, or?
So everything is based on the catalog. So if you have a catalog of earthquakes, which tells you when the earthquake happens, it means that you can take this information and look it into data, and you extract the earthquake that that is going to be part of your database. But you can think in the other way around. So all the times intervals where there is no earthquake, it's a noise. So basically, to collect the noise from your data, it just means that you have to look into time intervals where you don't have earthquakes. And that's basically what I did. So I went back in my data, and I specifically defined a function that will scan the earthquake catalog and look at the specific periods of time when there is no earthquakes. Of course, there are other problems. I mean, there are other noise. There are a lot of noise in seismological data from anthropogenic noise, some instrumental noise. And the point of the noise database is to catch all these possible other noises that are not earthquakes. So that's why it was kind of easy to build up this part of the data set.
Got it. Interesting.
Yeah.
I don't know a lot about seismology, so I've learned a lot here in your presentation.
I hope I was clear enough, but not too quick. I mean, like, I hope I explained what I wanted to say very well.
Yes, you did. We don't have more questions for now, so I'm going to start finishing the presentation. And I would like to thank you very much, Josipa, for for being with us here today. Your presentation was amazing. Thank you very much.
Thank you very much for the invitation.
Yes, yeah, now I'll open up for you to give some final comments, if you like.
Okay, final comments. I didn't think about that. Well, I would say that, machine learning in general, it's quite interesting topic in my personal point of view, and that people should not be afraid of the, coding part or all the challenges. If you're motivated, I think it's possible. And particularly in seismology, there are many things that can be solved, tackled, challenged, and so just go for it. And if you need, for example, if somebody of the people who are listening now are interested in particular in seismology, feel free to send me an email. I can give out some references, like if they are particularly interested in some topics. I mean, I will try to do my best. So.
Thank you. We actually received another question now. As for Mariana as well, she said there was an excellent presentation, very interesting, important, and she's wondering if CNN is being used in another geophysical application that you know of.
Particularly CNN. Let me think. Personally, I don't know. I know that CNN has been used for this particular problem, so like the earthquake detection, and it has been solved in the different ways. So using CNN to solve earthquake detection problem in different ways, but I don't really have like a knowledge of the other areas. But personally, I don't know why not, because CNN can be, for example, the layers can be 3D, 2D, 1D. So it means that as an input data, you can use time series, you can use, figures, or I mean, any kind of, let's say, 3D input data. So there's no reason why not. I'm sorry, I don't know the other applications.
Yeah, but I'm pretty sure that it's being applied in a lot of areas, right?
Yeah, I'm pretty sure. I just don't know. Like, I've been more like into detection, so that's it.
Well, now I think we'll finish the questions. I hope we don't receive more in this time we're finishing. But thank you again, Josipa, for your presentation and for your time here with us. And I'll finish the lecture for now.
Okay. Thank you. Bye-bye.